these are the graphs for the, question 2, 2015. So this is what you're given, right? And you're told this point is 0, 2, and then 2, 4, right? So the x-axis is going from 0 to 4. Well, in mine, just to have, some cushion, I go from, I'm sorry, the x-axis was going from 0 to 2. I like to have some cushion, so go half a unit before, half a unit after, and then, same with the y, right? And when you do that, you get this, cute little curve like this, and you can see, right, if I put it like this, you can see that basically, this one here is g of x, right? So this is g of x, and then this is f of x. Go ahead and write that because,
How did you figure that out?
Well, because here, from the graph here. Okay, go ahead and write that because later on, you don't want to spend time on that. Okay, so now it says, let f and g be functions defined as this. Let R and S be two regions enclosed by the graph. Find the sum of the areas of regions R and S. So first, what I need to find is this point of intersection right there. So let me just go ahead and do that. Menu, analyze graph, intersection, and that's that point there. And immediately when I do that, I'm going to write here that that's 1.033, comma 2.401. And then also, just go ahead and store that. What happened? Sorry. Store that as A. Enter. All right. So now you're ready.
What do you hit to make it?
You're set.
Control plus makes it expand, right?
Yeah.
Just store it just to make it faster, basically.
Yeah. And not just to make it more precise. Yeah.
Why does it get more decimals?
I wouldn't put in decimals because what if you made a mistake in like punching in the wrong number? It's so much better. Yeah. Okay, so now you want the sum of the areas. So what you need to show here is, because you're given the functions, you just need to show, okay, so first you say, let A equal to 1.0328. All right, I just went to one more decimal place. Okay, and now for part A, you say 0 to A, g of x minus f of x dx plus a to 2 f of x minus g of x dx.
Why did you do it to an extra variable? Like to 1.0328?
Just to cover my bases, that's it.
Is it okay?
Just to cover my bases.
Huh?
Just write the number.
What?
Instead of writing A, I write just the number.
I guess, yeah, it's fine. Yeah, it's fine. So now, okay, so look. I just want to move this here. There's a couple ways you can do this. Now, if you want the sum of the areas, it doesn't matter how you put it in your calculator, right? So I want to show you one other thing. Here, if you go to Menu, Analyze Graph, and if you want, choose Bounded Area number 7. All right, go ahead and do that, everybody, because it's kind of tricky when you're doing it by hand yourself. So go ahead and do this. Okay? Bounded Area. So now look, you're going to go here, lower bound. Look, if you can get your cursor just right, you can kind of like traverse the curve. And if it says intersection point, that's the right point, right? Like point on. And then if you just sort of like traverse, sometimes you get this that says intersection point. And then you want to go to, look, if you're just on the curve, right? And if you go to if you can find intersection point here, and then somewhere it puts in the total area, right? So for me, that's the total area. Was everybody able to do this? I need you to take a minute and be able to do this. Huh? F of x and Jonathan. F of x minus g of x. You don't, okay, it's that squared. Now, you don't have to write this step. It's good to write that step. Let them into your mind. Now the volume is gonna go from a to 2, f of x minus g of x squared, all right, dx. And so here I'm actually gonna go into, so I'm gonna do control, add a page, add a calculator, and I'm gonna go integral from a to 0.
The area, but can't you just square that number? Of
Yeah,
the
but it's
integral
not
from before?
No,
Because we found what.
no. That was the area of the whole thing.
No, but I did it. What? I have both values. Like 0.9974 is the left is R, and S is 1.0069. So I know that I already got S.
Okay.
Can I just square that?
As long as you can show everything perfectly well and you can justify your work, then you can do that. But you need to show everything in like perfect clarity.
Isn't it F2 minus F1? Because F2 is.
No. This is S. Let's see.
No, F1 minus F2.
You did A to 0. You did A to 0 instead of A to 2.
That was my fault.
All right. So it's 1.283.
Oh yeah, my way would have gotten it wrong answer.
Yep. So let's H be the vertical distance between the graph of F and G in region S. Find the rate at which H changes with respect to X when X is 1.8. Here is another one, another example where you have a very traditional looking problem, A and B, you've seen this a billion times, and now they throw C in there, to set, to see how much have you understood. So C, what I want is the rate of H, okay, with respect to X. So what I'm looking for is DH dx. That's what I want. So I want dH dx, which is d dx of, they said H was the vertical distance between F and G in region S. We already found that. It's f of x minus g of x. Right? So that in the parentheses is H. Now, if I want the derivative of that, well, that's just f prime of x minus g prime of x, but we want this to be evaluated at x equals 1.8. So really what I want is f prime of 1.8 minus g prime of 1.8, okay? And that's also a calculator problem. So I go in my calculator, and yes, there are, more than one way to do this. What I want to do now is menu, calculus, numerical derivative at 1.8 of f1 of x okay, right? So you can do it in a couple of ways. That's that. Minus, I'm going to do the whole thing again, right? You could also,
You just do F1 minus F2.
no, this way. of f2 of x. All right, and that's negative 3.812, okay? When you did this, right? Minus. You could also have gone up, copied this, Control C, drop it here, Control V, and then change the F1 to F2. That could have also worked. Okay? That could have also worked. Our velocity is given by a differentiable function v. Selected values of v are given. So t is in minutes, v is meters per minute. Use the data in the table to estimate the value of v prime at 16. V prime at 16 will have fallen here, so I'm going to take these 2 points and just do y2 minus y1 basically. So v prime at 16 is equal to, now you have to show this step. Over 20 minus 12. You have to show this. Then put in your numbers. This is a non-calculator section, so you have to do this anyway, right? And then that's 5 meters per minute, what? Squared. This is meters per minute divided by minutes, meters per minute squared. B. Using correct units. Here we go. Explain the meaning of the definite integral that in the context of the problem. Then approximate the value using a Riemann sum with 4 subintervals. Okay, what is that? The meaning of this?
Displacement. The total.
It's the what? The total.
Of the velocity.
Say it again.
The total
Displacement of a velocity function a lot from the, no, it's not that.
Not displacement.
Is it total distance on the phone?
It's absolute value. It's the
amount of distance
total distance. The total distance.
Johanna has traveled
So you
in
do the travel.
40 seconds.
in 40 seconds. No,
In 40 minutes.
Okay,
in
so
40 minutes.
is the total distance. Now it says using correct units. So it's the total distance in meters Johanna travels, or traveled by Johanna, whatever. Now you can say over the interval of 0 to 40 minutes, or you can say from 0 to 40 minutes. Don't get skimpy with your words.
Will we mark off for writing min per minute?
No. Okay.
You know your process.
Now, Riemann sum. So now we say, okay, so this is equal to, okay, so now we got to do the Riemann sum. Basically, if it's absolute value, right, if it's the right Riemann sum, so first we're going to do 12 times, it's the right Riemann sum, so I'm going to start with the 200, plus 20 times 240. Okay, here's the deal. Plus 4 times, now this is total distance, so that negative 220 has to switch to positive 20. That's the difference because it's absolute value.
Why 4?
Because from
Well, then
24
it
to
shouldn't
20.
be 20, it should be 20 times 12, which is 8. 8 times 240.
It should be 8 times.
Also, you put the intervals from 0 to 4. Is that because there's 4 subintervals, or did you mean to write 40?
40.
Okay.
So here,
The value around all of them is technically its absolute value because it's the same number.
what?
Because absolute value applies to all of them.
All of them.
Yeah, so it should be right it for all of them as the first step.
You just put an absolute value around the
No,
entire
no.
thing.
Okay.
No,
Here
I
it
meant
is.
each individual one.
Each individual one. Okay. The point of this problem is that each individual point has to be positive. So they're looking for, did you switch that 220 to positive 220? All right. You could also do this, right? But it's not necessary as long as you switched the sign. Okay? And then this one, you have to do some quick math here. So this is 2,400 plus 8 times 240. You have to do some mental math. 1920 plus 880 plus, now, okay, so this is 16 times 150. The way I would do it is 15 times 15 is what? 225. 225. Sorry. But then this is 16 times 15, so it's another 15, 240. Right? That's how I would do it. That's the quickest way for me to do it. So it's 2,400. So if it was 15 times 15, it would have been 250, but it's an additional 15, 240 times the 10. All right? And then all together, that's 7,600 meters. C. Bob is riding his bicycle along the same path. Okay? For 0 to 10, Bob's velocity is modeled by this, where t is measured in minutes, and BFT is meters per minute. Find Bob's acceleration at time t. So acceleration is b prime of t, and that's 3t squared minus 12t plus, that's it. B prime at 5 is 3 times 25 minus 60. 15 meters per minute squared. D. Based on the model B from part C, find Bob's average velocity during the time interval. So now look at this. This is already the velocity. You want the average of this. That's the average value integral. Right? So yes, so average velocity is 1 over 10 from 0 to 10. I can imagine a common mistake here will be
10 minus.
that a student will do, b of 10 minus b of like y2 minus y1, because that's how we found average here, right? They will think, that's what you need to do here. So that's going to be 1 over 10 t to the 4 over 4 minus 2t cubed plus 300t evaluated at 0 to 10. So that's 1 over 10, 10,000 over 4, minus 2,000 plus 3,000, right? So what's 10,000 over 4 these days?
25,000.
2,500 divided by 10, that's 250,
3,500
minus 200 plus 100, 300. 350, what are the units?
meters per minute.
Meters
velocity,
per
just
minute.
meters per minute. Like it was normal velocity.
Yep. So look, this is the velocity, right? That was meters per minute. The dt is times minutes. Then the 1/10, that's divided by minutes. So you end up with meters per minute. Do you see that?
Also, it says average
Dimensional
velocity.
analysis, right. Listen, you know,
Whatever
like
way it works.
whatever works. You might get stressed, confused, disoriented, hungry. I don't know.
I always get hungry.
All
During
the
my
above.
SAT, I was like, oh my god, I need to eat.
I get very hungry when I teach like a couple periods a day because talking wastes a lot of energy that you don't think about. Okay. Consider the differential equation slope fields. 2x minus y. Again, when I see this, I think to myself, it depends both on x and on y. Okay. So, on the axes provided, sketch a slope field for the differential equation. Okay, so this one here, let's start at the top. 0, 2 is -2, right? This one here is 0, 1. Again, you don't have to write any of that stuff. All you need to show are the dashes or whatever. So 0, 1, that's -1. And then here is +1. Right? So then what they want to see is basically that, like, you know, these have the same slant, and then this one has more of a slant, right? That's good enough. And then here it's 0. And I believe here it's +1, and then here it's +2. Now, number 4, part B, that's one I haven't seen in a while. It used to show up a lot before. All right, so find d squared y dx squared in terms of x and y. Okay, fine. So basically we just want the derivative of that. So d squared y dx squared is equal to d dx of that. Right? So that's going to be 2 minus dy dx. But what is dy dx, you say? It's 2x minus y. So d squared y dx squared, you can even leave it in that form, is this basically. Okay. Now, determine the concavity of all solution curves for the differential equation in quadrant 2. In quadrant 2, what is the concavity? Concave up is when f double prime is positive. When f double prime is negative, it's concave down. In quadrant 2 is where x is negative, y is positive. Correct? Okay? So, you say in quadrant 2, x is less than 0 and y is greater than 0. Which means 2 minus 2x plus y. So let's think about it. If x is negative, now we have positive, positive, and y is positive, all positives. Right? So that whole thing is positive. Therefore, oh, you know what? Wait. I'm going to write one more thing. So d squared y dx squared equal to this
Oh, you have to say.
is positive. So since you've established that the second derivative is positive, you can say that all solution curves are concave up. Isn't that clever? These are my, like, these people are my heroes.
Give me a refresher of what the symbols meant. I know the bottom
This means it implies,
implies.
this
then
means therefore. Let y equals f of x be the particular solution to the differential equation with initial condition f of 2 equals 3. Okay. Does f have a relative minimum, a relative maximum, or neither?
Wow.
Okay.
All right.
Where do we get relative min or max? When what happens?
Zero.
What does the graph look like when we get min or max?
Slope.
Yup. Okay, I have a verbal and a hand gesture. Both mean the same thing. So basically, when something switches from increasing to decreasing or vice versa, or when f prime is 0, right? When it has a horizontal tangent. So let's see here. What is the derivative at 2 comma 3? So what is dy dx at 2 comma 3? Well, dy dx is 2x minus y. So
How did you realize that this is related to the previous problems? Because it just says let y equal f of x.
yeah, but this whole thing is for problem number 4. So that's what I was saying before, is once you read this problem, you have to like get into this is the only world that exists now. You know, we're in the world of this differential equation, right? The sun like sets and rises here.
Yeah, so every time it says differential
Yep.
equation, it's referring to the same equation.
Uh-huh. So dy dx is 1. Slope is 1. So we say since dy dx is not equal to 0 at 2 comma 3, there is neither a max or a min. Okay?
I like that.
Mm-hmm. They like seeing little notes. I'll tell you about one problem after this one, D. Okay, find the values of the constants. Oh yeah, this one was a good one. Find the values of the constants m and b for which y equals mx plus b is a solution. Okay. Yep. Okay. So, if this is a solution to that curve, that means all the slopes are the same, are equal to each other, right? All the slopes have to be equal to each other. Okay, so let's put our phones away for a minute. So, dy dx, what's the slope of this, mx plus b? Yeah, so dy dx is equal to here, d dx of mx plus b, which is equal to m. But our global dy dx is equal to 2x minus y. Yeah? That means m has to equal 2x minus y. Now, I need to solve for m and b. I have m here, and then I've got x, and then I've got y, and then this is not getting anywhere. I have way too many unknowns here, so why don't I substitute a little bit? So why don't I say m is 2x minus, because I need m and b to show up more than I I have right now. Y is mx plus b, right? So that means m is 2x minus mx minus b. Okay, I don't know what's happening here. You know what? Let's just set everything to 0 and see where we get. So 0 is 2x minus mx minus b
But mx is 0.
minus m.
Oh, sorry. But you said m to 0. Just subtract it.
Okay, I still have that pesky little x. Okay, so why don't I factor out a pesky little x? And I get x times 2 minus m minus b plus m, like that, right? Now you're asking me, how am I supposed to know to do this? And the answer to that is, this is a tricky question. This is a tricky question. This is why we do this, so you have exposure to all the sorts of stuff. When I say there is always that one that they threw out of left field, this is like one of those, okay?
It's like out of the bullpen.
Yep. So now, back in the day, when we did partial fraction decomposition and pre-calc honors, do you remember there was one part where we matched like coefficients where it was like
and then you
x?
did the same thing in the parentheses, and then you
Yes.
just switched it to two things.
So on the left-hand side, what is the coefficient of the x?
0.
0, because there is no x there. So that means,
Oh.
so you say, so look, remember like way back in the day, we had like 4x squared plus 3x equal to a plus b x squared plus cx. And we said the coefficient of x squared is the same as the coefficient of x squared. Remember?
This is really advanced.
This is a, yeah. So
This is not something
we basically say 2 minus m is equal to 0. And then what's the constant term on the left-hand side? 0. So b plus m is also 0. So if 2 minus m is 0, m equals 2. And then here,
I don't understand how you did.
b equals negative m. So b equals negative 2.
Yeah, there's no way I would think of doing this.
This is a 3-point problem. You get 1 point for this, 1 point for this, and then 1 point for the rest. So look, it's very, very fairly distributed.